This is part 2 of our chilled water design strategies for chill beam applications. In this series, we're going to talk about modifications to a typical chiller plant that are commonly done for chill beam applications. First one we're going to talk about is some form of waterside free cooling. Now, we have a situation here where we've got the chiller plant. We're showing you variable primary flow. This could be primary, secondary. It doesn't matter for the discussion. And we, in the summer, in the cooling load season, we would make somewhere between 42 and 44 degree water to service the ventilation units. This water has to be cold enough to be able to do the dehumidification that the building requires. And then we would have a second loop that's servicing the chill beams. That's these characters right here. That loop's going to be above the dew point of the space, so it's typically 57 or 58 degrees, and we're sending water out here that is warmer to service this because we're only going to be doing sensible cooling out at the chill beams. Now, these chill beams are going to see a cooling load even in the winter. If you're in the core of the building, in a large building, even in a cold weather climate, we're still going to have sensible heat gains in the space that we have to manage. And so we need a source of 57 degree water, even though it's cold outside. We would love to shut down the chiller plant and find a way to do that with free cooling. If you're going to look at air-cooled chillers, this is actually a pretty straightforward thing to do. You can source air-cooled chillers that have integrated free cooling. There effectively is another coil in here that these fans would pull air across so that they could run the evaporator water through the water coils, cool the air, that water down using the fans in the fan deck, and supply that back to the building without having to run the refrigeration to do that. In fact, a lot of them are smart enough to look at these loads in what we would call in series, so that we first try to cool the water down as much as we can by just running it through a coil and blowing air across it. And if we can't get it down to our supply water temperature, then what we would do is use some mechanical cooling to finish the job and get it down to 42 degrees. And all of that is in a packaged unit with package control, so it's very straightforward. In this example, though, we're going to look at a water-cooled chiller plant. So again, we're still showing you a variable primary flow system. We're not showing you the cooling tower loop, but these chillers would have condenser water coming from a cooling tower plant outside of the building. The chillers, of course, are rejecting their heat to the cooling towers. A cooling tower temperature would be optimized to improve the efficiency of the chillers. Design days are usually 85, 95 temperature, but in shoulder weather, lowering this chiller cooling tower plant down closer to 65 degrees, if the outdoor air wet bulb will let you do that, will greatly improve the efficiency of the chiller plant, and so it's something to consider. And so we're starting to get pretty close to making water that we could use out here at the beams. Now, as the air temperature drops through the fall and it gets cooler and cooler, we'll reach a point where the outdoor air dew point matches the space dew point. And at that point, we no longer need any kind of mechanical cooling. We're just going to bring outside air into the building. If we have to temper the temperature a little bit, maybe warm it up because it's actually too cold, we would do that with some kind of energy recovery device in the air handling unit, drawing the heat from the return air. And so you're no longer going to have a requirement to produce 42 degree water. You could reset the temperature from 42 to 57 at that point, greatly improve the efficiency of the chiller plant, but you'd still be running the chillers and you'd still be consuming energy to do that. So alternatively, what we'd like to do is to add a waterside economizer, a heat exchanger here. You are going to want a heat exchanger. This is going to be a cooling tower loop. It's going to be open. That water is going to have water quality work that has to be done. You want to separate it from your clean water that's inside the building. And so now what we can do is use our cooling tower plant over here and speed up the fans to cool it down so that we can make 57 degree water to supply to the building. And that 57 degree water is really nice. I mean, that's a lot warmer than most chiller plants requirements because we only have to do sensible cooling out here. It's going to increase the number of bin hours, the degree days where you could service the building with waterside free cooling, right? Because that's a lot warmer. I'm going a lot more hours wherever your city is that would allow you to use cooling tower water to achieve 57 degrees. So if we zero in a little bit about what's going to go on in this control sequence in here, you see we've got water coming to and from the cooling tower. We can use that to cool the water down. Our goal is to have a 57-degree supply temperature out to the chill beams. It's going to come back around 64, and then we would use the tower water to cool that back down to 57. If this actually overcooled and made the water cooler than that, you could mix some 64 degrees with that 57 degree or whatever water temperature we get from here, maybe 53 or 54, and to get it back up to the 57 degrees. In the dead of winter, this thing would be 100% bypass. The chiller plant would be completely shut down. There would be no need for chilled water for the air handling units because it would be cool enough outside that that wouldn't be a challenge. And so this loop would just run like this, and the main chiller plant would all be shut down. In shoulder weather, you might be able to do some free cooling here and mix it with the if the chiller plant's online. If we may not be able to get it all the way down to 57 degrees, we could introduce a little bit of chilled water from the chiller plant to do this thing. You need to do a little bit of thinking about what temperature you're going to ask the cooling towers to operate at. When you're in economizer mode, you want the cooling towers, that water's got to be colder than 57 degrees. If you have a 2-degree approach on your heat exchanger, that means this water, you've got to pull it down to at least 55 degrees, which is pretty cold for chillers. So you would need to think about if you're running the tower plant to make 55-degree water for free cooling, but you want to run some mechanical cooling, just you'll need to slow down, think about how you're going to actually make that water a little bit warmer for the chillers themselves. 55-degree water would be pretty cold. Check with your chiller manufacturer. Some other things that you see people do when we start talking about chilled beam design and chilled water plants to service that. One consideration would be to separate the loops, right? You know, we have a system in here that would be servicing the chilled beams. We only need to make 57-degree water. If we could set up a separate loop for that, it would have a significant impact on these chillers. You could pick up 25 or 30% of the efficiency on the chillers just because in the dead of summer you would only be making 57-degree water instead of 44. So a huge improvement on that. And having a dedicated loop for the chilled beams, and then you have a second loop where we're going to make 42-degree water, and we're going to send that water out to the air handling units. It's going to have to be in that 42 to 44-degree range because we have to do all the dehumidification for the whole building down in here. Now this looks really nice and might work well in an energy model. In a practical sense, to set up 2 chiller plants with multiple chillers completely separated is a fairly expensive design, and it would take a fairly large project to justify the capital cost to do that. So an alternative to that would be to look at something in here where we have a dual loop system, and we call it kind of an N+1, but let's look up here. We have 3 chillers all set up in here. They're all valves so we can change the flow. And right now, this is just a different layout of what we saw on the last screen, right? We have one chiller that's servicing the chilled beams. It's making 57-degree water. It's enjoying a very small lift, and so you're going to get a very high COP. And that system is running around in here, doing its job, and servicing the chill beam loop. We have another chiller up here that is pumping water up out to the air handling units, and it's running at 42 degrees to do the air handling units. So the loops have been separated, and we allow part of the chiller plant to operate at a more efficient point. So now one of the things we could do is, what happens if we have an issue with this chiller? Well, we could have a crossover chiller, this one that was available to us, and in fact if we needed both chillers to do that, we could operate both chillers to service this load, and through the valving we can allow this chiller to go and service the ventilation units and make 42-degree water to do that. And then of course What if it went the other way, where we need to take this chiller off for service? We could again use our crossover chiller, reset its chilled water supply temperature from 42 to 57, and then switch the valving to allow it to service the chill beam. So if you are going to look at, you have a large enough system that you want to consider running 2 separate loops, but you are looking at how you can share chillers and equipment so that you can get some kind of redundancy or resiliency built into the chiller plant. This is a good approach to allow you to mix and match chillers to share the load out. And that way, if you have an issue on one loop, you're not going to completely shut that loop down. Now, another way to look at chiller plants, and this might be more attractive on a smaller chill beam system, is that you go and dedicate a loop to the chillers. You dedicate the chillers to just the chill beams, and you separate your ventilation units and make them standalone. So some kind of, most likely some form of integrated DX. And that does a couple of things for you. So it allows you to simplify your chilled water system significantly. It's only going to be a 57-degree loop. You're going to get fantastic efficiency in your chillers. That's going to be very nice. You could bolt on some Waterside free cooling, either having it integrated into the chillers or through a heat exchanger to the cooling towers, and take this chiller plant offline once you could produce 55-degree water from your cooling towers. So if you have a 7 or 8 degree approach on your cooling towers, you want to make 55, somewhere around 46, 47 degree dry bulb temperature outside, wet bulb temperature outside, you would be able to produce the water that you need just using a cooling tower and shut down the chiller plants. Over on the ventilation system, you make this a standalone piece of equipment. So it would have integrated, heating and cooling. It'd be great if you had a heat pump system, because then it'd be kind of a carbon-free solution. You're not burning any natural gas. Now this piece of equipment, its efficiency is going to be less when it's hot outside, right? This is effectively now air-cooled DX versus a nice big fancy chiller plant, but this load drops off very quickly and is quite linear to your outdoor air conditions. So as soon as it starts to cool off outside, you're going to see a big improvement on the COP. And this system is not likely to run once the dew point of the air has been met, which is somewhere around 56 degrees. So once you get to that temperature, you're going to shut down your refrigeration system and just use the outside air. It might run in heat pump mode, but it's probably not likely to happen. In most cases, we design these systems to deliver 55-degree air, and most parts in North America, with good energy recovery, you can warm up outside air up to 55 degrees just by borrowing the heat through your energy recovery device, and you could actually, you'll find that you'll run almost no hours in heat pump mode if you're supplying 55-degree air. If you have a warmer design, 60, 65, or 70 degrees, you will have some hours on your heat pump, but that's straightforward to do. Of course, if you have natural gas in the unit, that would be straightforward as well. So let's talk a little bit about driving to a carbon neutral, very high performance chill beam system. And a chill beam system is going to make your short list of highly efficient HVAC systems for a lot of building types. So if you're driving to a very high energy performance building, chill beams are going to be an attractive solution. If you want to drive to a carbon neutral building, one that doesn't require on-site burning of natural gas, you can do that with a chill beam system by looking at simultaneous heat-cool chillers, sometimes called heat recovery chillers. So let me just show you a couple of types that are in the marketplace. This is a water-cooled system, and effectively it has 6 connections. It has a chilled water loop, you can see here. It has a hot water loop, and then it has a source loop. So what this chiller is going to attempt to do is that when there is load both on the heating and on the cooling side, these 2 loops, it will extract the heat out of the chilled water loop. It's going to cool that chilled water back down, and it's going to use that heat to make hot water on this loop. And that means that you can move heat from the core of your building where your chill beams are going to be running and cooling, and they're going to add heat to the chilled water loop, it gets back to the chiller plant, we are going to shift that heat into the hot water loop and use it on the perimeter chill beams, which could easily be in heating mode because of the skin loss through the building. And so this HVAC system will allow you to move energy from where there's a surplus of it in the building to where there is a need for it in the building. That's incredibly energy efficient, and we did it without having to burn any natural gas on the job site. Now, if you have more energy than you need, which would be the summer, where you have almost no heating load, lots of cooling load, then you can the energy will be dumped into this green loop. This could be connected to a geothermal loop, and now you would be talking about net zero energy design buildings. This is about as high performance as you're going to get, because effectively we would store that heat in the ground in the summer. You would raise the temperature of the ground outside 2 or 3 or 4 degrees, and you would extract that heat out in the following winter to heat the building back up. And so this is really about the best performance you're going to be able to get in a building type. This could also have been hooked to a cooling tower, and that heat could have been rejected. In the winter, you might find out that you're not putting enough heat into the system, and so we need a heat source. If this is geothermal, we would be warming this green loop up with the ground loop, and then the refrigeration plant would be raising its temperature from 35 or 40 degrees up to 110 degrees, so that we have a hot water source that we could use to do the heating in the building. So very nice system. This is an air-cooled version. What you see down below, you can see again you've got 2 loops. The green one has been replaced with the coils here and the fans, because this is it's being connected to the atmosphere. So it'll do all the same things. Let's look at a system layout with one of these. So here we have an air-cooled chiller, so it's going to be a 4-pipe. From that point of view, we start with the red and the blue. This is our chilled water loop. We're sending water out to these coils at the air handling units in the summer. We can do the dehumidification. We use a mixing valve in here to run a secondary loop at 57 degrees out to the chilled beams. And so this loop, we're adding energy from the building into it. So we now have a low-grade energy source of 60-degree water. And if we had some heating load somewhere in the building, maybe more in the fall, the refrigeration plant in here would extract the heat from this loop, and rather than rejecting it to atmosphere, would actually use it to heat the hot water loop. And so this yellow-orange loop in here is the chilled beams and potentially the air handling units, hot water coils. And so now we're going to send out hot water somewhere between 110 and 120 degrees would be fine. We can heat the perimeter zones, so we could be collecting heat down here in the core, using that heat through the chiller plant to heat the outside beams. That heat would go into the air. This water is cooled down. The yellow line comes around through the pumps, and we put the heat back in to warm it back up. So this is a heat recovery system, air-cooled style, that allows you to move heat from around in the building. If you have a surplus of the heat, you reject it to atmosphere. If you have an absence of heat overall in the building, this will run in heat pump mode, extract the heat back out from the air, and use that to heat the beams. Now we can do the same thing with a water-cooled plant. So the chillers would change. They'd be now 6 connection chillers like we just discussed. You'll see everything that we saw on the chilled water side is one set of loops. Where possible, we're going to take that heat and use it. If we have a demand for heating, we'll take the heat out of the building, raise its entropy, raise its temperature, and deliver that that water out to the building to do the heating. Could be in the around the perimeter. If we have a surplus of heat, we would dump it into the green line. It could go into a ground loop. We have marked here. We could store that energy in the ground during the summer, and then when we got around in the winter where we don't have enough heat in the chilled loop to meet the heating load, what we would do is take that heat, whatever we needed to from this loop, and if we needed more, we would grab it from the ground loop to provide enough energy for this space. Now, in a lot of commercial chilled beam designs, you're going to be in a net heat gain all the time for almost every hour that the building is operating, which simplifies it greatly. And you really do want to say, hey, I'm going to take that heat from the building, wherever it's being generated, and shift it to where I need it in the building, generally moving from the core of the building out to the perimeter. And so this is a very good way to take a very good system, a chilled beam system, and make it one of the best systems that she could design by being able to move the energy from one side to the other. And it has the added benefit that you could do this carbon-free. So that's a little bit about chiller plant designs focused on chill beams. Thank you very much.